Hi everybody, and welcome to this short video about bases for vector spaces. I will start with a question. Do you know how your computer monitor works? Well, if you magnify it, you will see that every single pixel is actually made of a little array of a red, a green and a blue spot. By properly adjusting the backlight to these subpixels, then you can blend them and reproduce every color picture you want. The reason behind it is that red, green and blue just constitute a set of primary colors, and by properly combining them you are able to reproduce the full spectrum of visible colors. So the role of these primary colors is totally analogous to the role of bases for vector spaces. And here we will give some proper mathematical definition. So let V be a generic vector space defined over the field F of scalars. We need to introduce some concepts. In particular, the first concept is that of a spanning set. Spanning set is just a collection of vectors belonging to V. So say U1, Un. So if you have your generic vector space, V, that you represent as a set, this will just be a collection of some elements, typically a finite number of these elements. Then something more important is the span of this spanning set, where this is in general a subspace of your vector space, and is defined by all the vectors in V that can be written as linear combinations of the elements of the spanning set. So here you may write V is equal to K1 U1 plus K2 U2 plus Kn Un, where in general the U's belong to the spanning set and the K's are scalars belonging to the scalar field. So as you see, this represents a subspace. So in particular, if you want to continue with the metaphor of colors, if you choose the spanning set to be red and yellow, then the span of this set will just be all tones of orange. Another notion that we will need is that of linear independence. So a spanning set is linearly independent if basically there is no redundancy in the set. So if no vector within the spanning set can be written as a linear combination of all the other vectors in the spanning set. So in particular, if you want an example like red, green and yellow, this is not a linearly independent set because yellow can be obtained by mixing red and green. Now we need to concentrate on two categories of spanning set. One is the category containing all spanning sets that span the whole vector space. So here you may have just enough to reproduce all vectors by linear combinations, but you may also have more vectors. So you may have some redundancy. So in general, there will be too many here. On the other hand, you may consider the set of all vectors of all spanning sets which are linearly independent. Linearly independent means that no one can be written as linear combination of the other. But in principle, you may have too few vectors to generate the full vector space. What we are interested in is just the intersection between these sets. This intersection contains what are called the bases for the vector space. So the elements in here are the spanning sets which contain just enough vectors, the minimal number of vectors, such that by linear combinations of them you can obtain any vector in your vector space. So a basis for a vector space is a spanning set which is linearly independent and its span coincides with the full vector space. We can give another example. So consider, for instance, the vector space of all the two-dimensional vectors. So if you want some set of vectors that spans the full space, you may think to a set like this. So for instance, vector 0, 1, 1, 0, but also 1, 1. These are enough to span the full vector space, but this set is not independent, because 1, 1 can be obtained by just adding up 0, 1 and 1, 0. On the other hand, you may have a linearly independent set, which is just formed by a single vector, like 0, 1 or 1, 1. But this will not be able to generate the full vector space. So if you look at the intersection between these sets, then you have the basis for the vector space that contain just two vectors which are not parallel to each other. For instance, 0, 1, 1, 0, but also 1, 2, 3, 4. So you see, two non-parallel vectors are just the minimal set of vectors that, upon using linear combinations, generate the full vector space. So these are all bases for the space. You may notice that we can have different choices for the bases, but they all have something in common. In particular, the number of elements forming each basis, it's always the same. In this example, is 2. This can be proven as a theorem for general vector spaces, and in fact this defines what is the dimension of the vector space. The number of vectors forming any basis for your vector space is defined to be the dimension of the space. For R2, the dimension is 2. For R to the n, the dimension would be n. Okay, so let's do an exercise. Consider as a vector space the space of all symmetric 2 by 2 matrices with real entries. So all the matrices A belonging to the space of 2 by 2 real matrices such that A is symmetric. Now let's try to construct a basis for this space. Well, you need to write down the generic element of this matrix that you can write in this form. A and B, generic real numbers on the main diagonal, and then the two of diagonal elements need to be the same. So this can be written in this way. So you may decompose it as A times 1, 0, 0, 0 plus B times 0, 0, 0, 1 plus C times 0, 1, 1, 0. So if you consider just the set of these three elementary matrices that I'm circling in blue, these are three matrices which are linearly independent, and by means of linear combinations you may construct a more general element of your vector space. So a basis for V is just formed by these three matrices: 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0. And from this exercise you learn that such a subspace has a dimension 3. Now if you can try at home to do the similar exercise when you consider the set of antisymmetric matrices, you should find that the dimension in that case is just 1. So given that any 2 by 2 matrix can be written as just the sum of one symmetric and one antisymmetric matrix, you have that adding up the dimensions, you find again what you should know, that any 2 by 2 matrix is in general specified by just 4 independent elements. So remember, just as the three primary colors, red, green and blue, form a basis for all the space of colors, in general any minimal set of vectors that by linear combinations are able to reproduce all vectors in your vector space and is a linearly independent set is what is the basis for your vector space. Have fun!